All right, so we're jumping ahead to section 11.4. All right, so what we mean by limits at infinity, just so we're clear to contrast with what we were talking about last time. Last time we were talking about the limit as x approaches a number. So here we're talking about the limit as x approaches plus or minus infinity of some function. So that's what we mean by limits at infinity, as x approaches plus or minus infinity. Let me make that look a little. And I want to start by talking about the graph of a function. So let's to introduce this topic. So let's look at f of x equals 2x over x plus 1. And we're going to sketch a graph of this thing. All right, so looking at this, we need to think about what our graph's going to look like. So looking at this function, what do we know about it? What's that? It's a rational function, okay? And what can we figure out about the graph? Let's look at the denominator. What can we figure out about what does the denominator tell us? Okay, so is there a hole? Do we have a factor that's in the numerator and the denominator that cancels? Oh, John? What's that? So we can figure out the intercepts and the asymptotes. We're not as worried about the intercepts here, but we can figure out the intercepts and the asymptotes. So the denominator tells about what kind of asymptote? Vertical or horizontal? Vertical. Because when the denominator, what happens, what can't we put in the denominator here for our function to be, we can't get a 0 down here because then our function's undefined. So what gives us a 0 here? X equals -1. So we're going to have a vertical asymptote at x equals -1. So I'm going to draw in my vertical asymptote. What about a horizontal asymptote? Do we remember how to figure out our horizontal asymptote here? So when the top is equal to 0, our function would be equal to 0. So let me give you a hint here. The degree of the numerator and the degree of the denominator are the same. So we'll talk about another situation, but in this one, the degree of the numerator and the degree of the denominator are the same. So what does that tell us about our horizontal asymptote? What? We remember? It's the ratio of the leading coefficients. So the leading coefficient in the numerator is 2, in the denominator is 1. So we have a horizontal asymptote at y equals 2. So we have a horizontal asymptote. And if I sketch in the graph, if I plotted some points, I would see that the graph looks something like this. And then on this side it goes this way. And we figured out which way it went by just plugging in some points over here, plugging in points over here. All right, so let's look at this graph. As x approaches -1, as we get closer and closer to -1, what is the limit? What is my function approaching? So what happens here? And here? Our function is unbounded. So as x approaches -1, what's our limit? Does not exist. As x approaches -1, the function is unbounded, so our limit does not exist. We're interested today, so this was what we talked about this the very first lesson, that when our function's unbounded, our limit doesn't exist. We're interested in the limit as x approaches positive and negative infinity today. So as x approaches positive infinity, what does my function get close to? Get close to the asymptote. Gets close to 2. And as x approaches negative infinity, what does my function get close to? Gets close to 2. Limits at infinity are talking about, they're asking about the end behavior. So we're interested in our end behavior. Our end behavior has to do with horizontal asymptotes. And we talked about that way back in chapter 2. So this is why I said we already know about limits at infinity, because we already know something about how to find horizontal asymptotes. Here we saw that the degree of the numerator and denominator were the same. So the horizontal asymptote was y equals the ratio of the leading coefficients. Well, that is our limit as well. Our asymptote is a limit. That's what f gets close to as x gets close to infinity, or as x gets close to negative infinity. So our limits at infinity are asking us about horizontal asymptotes. The rules for finding limits of at infinity are exactly like the rules for finding horizontal asymptotes. So we can think of them as being the exact same thing because they are the exact same thing. Horizontal asymptotes tell us what our function gets close to as x gets really, really large or really, really small. All right. So our basic rule for limits at infinity. So we're going to, for the most part, we're going to think of our limits at infinity with these rules about horizontal asymptotes. But I also want to show you how to work with them algebraically or analytically. As the book will say, show that the limit is this algebraically, or show analytically that the limit is this. So our basic rule is that the limit as x approaches infinity of 1 over x to the r, where r is some real number, equals 0. As x gets really, 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 really large, x to any power gets really, really, really large. And when I divide a number by a really, really, really large number, I get a really small number. And as that number gets bigger and bigger, this number gets closer to 0. And if my function is defined as x approaches negative infinity, 1 over x to the r, if we're not taking an even root, so a square root, a fourth root of a negative number, as long as this is defined, this equals 0 as well. So this is our basic rule for showing that limits, for finding limits at infinity algebraically or analytically. And I'll show you how we use them, how we use these rules when we do our examples. So that's the kind of the gist of the lesson today is our limits at infinity have to do with horizontal asymptotes. And this one rule, it really is our rule for deciding what our limits at infinity are. All right, so let's look at an example. So that's all I want to do is look at examples of how we apply these ideas. So let's find the limit as x approaches infinity of 3x to the 4th minus 5 over x to the 4th. So the degree of the numerator and the degree of the denominator are the same. So what does that tell us about our horizontal asymptote? I'm just going to write it as HA. As 3, so our horizontal asymptote is at y equals 3. That's the horizontal line, y equals 3. So our limit equals 3. Because as x gets really, really large, our function gets closer and closer to 3. Y gets closer and closer to 3. To show this algebraically, all we need to do to show this algebraically, divide everything by the highest power of x. So this is what we're going to do to show this algebraically. So let's go through those steps. So we have the limit as x approaches infinity. This is how we would simplify this algebraically. Divide by the highest power of x. So the highest power of x is x to the 4th. So when I divide 3x to the 4th by x to the 4th, I get 3. Divide 5 by x to the 4th minus 5 over x to the 4th. And then we're going to divide in the denominator. We're multiplying the numerator and denominator by 1 over x to the 4th. So we get over 1. The limit as x approaches infinity of 3 is just 3. The limit as x approaches infinity of 1 is just 1. And the limit as x approaches infinity of negative 5 to the 4th. So we have a number over x raised to a power. That limit is 0. So we get this as 3 minus 0 over 1 equals 3. So this is how we would show that this limit is 3 algebraically. But we know that's the case because we know it has a horizontal asymptote at y equals 3. But your homework questions will ask you about the limit, and it will say verify this algebraically or something like that. All right, questions on what we did here? All right, let's look at another example. Let's look at the limit as x approaches infinity of x minus 1 over x squared. So here, the degree of the denominator is greater. Do we remember our rules for horizontal asymptotes? What the fact that the degree of the denominator is greater tells us? Our horizontal asymptote is at, what is it? 0. Horizontal asymptote at 0. I'm going to say HA at y equals 0. So this limit equals 0 because as x gets really big, our function gets closer and closer to 0. And if we wanted to show this algebraically, I would divide everything by the highest power of x, divide by x squared, so this is the limit as x approaches infinity. X divided by x squared is 1 over x minus 1 over x squared, and x squared divided by x squared is 1. And the limit as x approaches infinity of 1 over x is 0. 1 over x squared, 0 over 1 equals 0. We call a function like this, a rational function where the highest degree is in the denominator, we call this bottom heavy. So this function would be a bottom-heavy function when the degree of the denominator is greater. Bottom-heavy functions, the limit as x approaches infinity is always 0. And that's because if our degree in the denominator is bigger, we have a horizontal asymptote at y equals 0. So if the problem asked you to limit and you told me this function is bottom heavy, the limit's 0, you're done. That's all you have to do. If I asked you to show or verify algebraically, you would show me this step. And that's all you would have to do. Divide everything by the highest power. And I talked to Miss Hine, the Calc BC teacher, about this because I said, here's how I talk about limits. And she said, that's exactly what I do. I talk about the horizontal asymptote and go straight to this idea of bottom heavy. So you'll be in a good place as you go to calculus next year. And I know Miss Cunningham and Mr. Grace do the same thing in Calc AV. All right, questions on bottom heavy rational function. All right, let's look at another example. Let's look at x, the limit as x approaches infinity of x squared minus, or x cubed minus 1 over x squared. So here, the degree of the numerator is greater. Do you remember what that tells us about our asymptotes? There is no horizontal asymptote. And for this particular function, we have a slant asymptote. So what does our function do if we have a slant asymptote? It's getting bigger and bigger and bigger, or the slant asymptote goes down, it's getting smaller and smaller and smaller. So our function is getting closer, is getting really, 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 really big, or really, 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 really big negative. So our function is unbounded. So what does that tell us about our limit? Does not exist. And we say D, we can say D and E instead of writing does not exist. So our limit does not exist. We have no horizontal asymptote. Our function is unbounded. So we can think of our horizontal asymptote as x gets really big, that is kind of like a boundary. It keeps our function from getting too big. But because this one doesn't have a horizontal asymptote, the function is unbounded. Limit doesn't exist. If we wanted to show this algebraically, divide everything by the highest power in the numerator, or sorry, not the highest power in the function. So we're going to say the limit as x approaches infinity. Divide everything by x to the third. So I get 1 minus 1 over x to the third over x squared divided by x to the third is 1 over x. And we get the limit, this stays 1. 1 over x to the third, the limit as x approaches infinity of that is 0. Limit as x approaches infinity of 1 over x is 0. So I get 1 over 0, undefined, does not exist. So this is how we would show it algebraically. We call this type of function, where the degree in the numerator is greater, top-heavy. When functions are top-heavy, when rational functions are top-heavy, the limit as x approaches infinity does not exist. So we can look at this rational function, say, oh, this one's top-heavy, the limit does not exist. And we're done. Then if the problem asks us to show algebraically, we would do this step and say that does not exist. So that's all there is to limits at infinity. Our functions, our rational functions, are either going to be top-heavy, bottom-heavy, or if the degrees of the numerator and denominator are the same, our limit's going to be the ratio of the leading coefficients. All right, a couple of important things. Remember what the rules that we're talking about here today have to do with limits as x approaches infinity. So we can't use this top-heavy rule, bottom-heavy rule if x is approaching a number. This is only for limits at infinity. And this rule for limits at infinity only applies to rational functions. So we couldn't, we'd have to do some other kind of argument if we had something like the limit as x approaches infinity of cosine x over x squared. We would have to do something else. We couldn't say this is bottom heavy, so the limit is 0. We'd have to make a different kind of argument. This limit does turn out to be 0, but we couldn't say it was because it's bottom heavy. And when we have more complicated functions than rational functions, we have to be a little more sophisticated with what we do. So you'll learn about that next year, and the year after that, and the year after that, probably, as long as you take math. All right, so questions about limits at infinity. That's all there is to it. We already knew about our rules for horizontal asymptotes, so we already knew about limits at infinity.
I like this.
You like this? You like limits?
At infinity.
At infinity?
At infinity, I do. I really do.
All right. Homework. All right, there we go.